Hello all, welcome. Thanks for being part of our Open AGI session. The part of AGI is AGI itself, and what we wanted to do as part of a broader workshop here is to invite top AI researchers, thinkers, scientists, and to talk about their vision for both the decentralization part and the AGI part. That's what this event is. And in the first panel, here, it's not so much a panel as inviting a few speakers from pure AI world to talk about their vision for what decentralization and AI look like. And in the very first one, we have two scientists, AI scientists, talking about their vision. One is Colin Ruffel. Colin Ruffel is a professor of computer science at University of Toronto. And the second talk will be by Wang. He's a professor of computer science and electrical and computer engineering at University of Texas at Austin. They both also have their industry and startup hats. One at FX Markets, Atlas, and Hugging Face with Colin. And we're very happy to have their vision, and the way we did is that we requested them to give record specifically for our event and audience what their vision is for decentralization and AI. And they're quite experts at it themselves.
Hi, my name is Colin Ruffel. Thanks for having me. I'm going to be talking a bit about some of the work that we do on my group, and this is work that aims to make it possible for a distributed community of individuals to work together to build powerful AI systems. So let's get started. So as many of you know, a dominant paradigm for building AI systems today is to use large language models. And what we expect large language models to do is to be able to perform basically any text-based task. So we want them to be general purpose. In other words, if I ask a large language model to do something like summarize the following article, then we hope and try to get large language models to be able to output the summary of the article. And importantly, what we expect is that we only need one model to do pretty much everything. We don't need a specialized model for summarization and another for paraphrase detection. We really want one single model, one single set of parameters that can do basically everything. And what I'm going to talk a bit about in this talk today is an approach for building similarly general purpose AI systems, but that takes a different path that I think has various benefits that I'll discuss. And specifically, the approach that I'm going to describe, I'm calling an ecosystem of specialist models. So what do I mean by that? I mean that rather than having a single model that we expect to be able to do everything, we have a huge collection of models, each of which is specialized in some way. Maybe it's particularly good at processing text in some particular domain, or it's specialized to some task, so it's very good at summarization and not very good at other things. And the hope is that if we have a big enough collection of these models, we get a pretty decent coverage of the kinds of things that people want to do with the AI system. But importantly, I also think there will be ways to make it so that such a system can actually generalize to new tasks. And that's something that I'll be talking about today. So even if we don't have a specialized model for some particular task or domain or setting, we can figure out a way to combine the models in our ecosystem in order to have our composite system be able to generalize to new tasks, to be general purpose in the way that we expect large language models to be. So let me talk a bit about this approach. And I'm going to talk about the approach by answering the following question: how and why should we build ecosystems of specialist models instead of monolithic models? And I'll answer this question in various ways. And the first thing that I'll point out, which I think many people know, but people don't talk about very much because it's very unsexy, is that specialist models are often cheaper, they're more computationally efficient, and they're sometimes better. And there are, I think, lots of examples of this holding true, scattered about, but one piece of evidence for this that is honestly pretty out of date now, but I still like to highlight it because it's work for my group that I'm proud of, was a paper that we wrote showing that if you took a very small data set and you fine-tuned a language model on that data set, if you actually performed training with that data, then the specialist model that was trained on that data set would outperform doing few-shot in-context learning with a large language model. And if you're not familiar, few-shot and context learning is where you take the small data set and you basically just concatenate all the examples in the data set and feed it as input to the language model. And this is, or it was, and still to some extent continues to be a common way to get language models to get large language models to perform a task, maybe with a bit higher accuracy. But in our case, we showed that not only does it work better to do fine-tuning, but also you can fine-tune a much smaller model. And when you use the model, you don't need to feed in the examples in context. So the whole thing ends up being quite a lot more efficient, about 1,000 times more efficient in this case. So another thing I'll point out when you're thinking about what an ecosystem might look like is that there are lots of ways that we could build such an ecosystem. One is, yeah, to just collect a huge diversity of models, different model architecture sizes, etc. But one promising way to build an ecosystem would be if each specialist model was actually a cheaply communicable update to some shared base model. And there are reasons that this would be advantageous. It's not a requirement, it just maybe would make things work especially well. And so let me describe what I mean by a cheaply communicable update. And for those of you who are familiar, I'm going to be talking a little bit about parameter efficient fine-tuning. And what this is it's a way of updating a base model without updating all of the model's parameters. Because one of the reasons people are afraid of doing training now is that they don't want to have to store an entirely new copy of the model's parameters every time they perform any kind of training. But in fact, the results that I just presented a moment ago, comparing few-shot fine-tuning to few-shot and context learning, those were results using a parameter-efficient fine-tuning method that we developed called IA3. And IA3 is notable because it only updates about 0.01% of the model's parameters, but in the experiments that we ran, we actually showed that it outperformed updating all of the model's parameters. So you can update a very, very small number of parameters and still get very good performance. And in subsequent work, we showed that you could actually further compress these updates. And specifically, the way we compress them is by looking for the largest changes and zeroing out the rest, and then quantizing those changes and only storing their sign. So basically, we have a consistent magnitude across all the changes and store the sign. And this saves space because now we kind of have a sparse update, and we only have to store the magnitude and the sign, which is the sign of each update, which is a binary value. And so we can get further savings in size, and ultimately, for a model with tens of billions of parameters, we can store an update, a parameter-efficient update that specializes the model to some particular task with only on the order of tens of kilobytes of storage. So if you want to have an ecosystem of models and have 10,000 of them, well, that's totally tractable if each of those specialist models is only tens of kilobytes. And you could imagine having all of those models all at once on a single GPU, for example, or at the very least on a single server. So just one way to do this, not the only way, but it solves maybe some of the system-style challenges and objections you might have. Okay, so now to describe a component of an ecosystem that I think would be especially important is the ability to choose the appropriate specialized model for a given query automatically. So why is this important? It's because when I use a large language model, I don't select which task I want it to perform, I just describe the task in natural language. And why is that important? Well, if I had to select the task, that would presuppose that I could only select one of a small set of tasks. If I want to be able to generalize to new tasks to perform, basically to be general purpose, I need to be able to describe basically anything that I want the model to do. So at the very least, we need to be able to choose the appropriate specialist model for a query automatically. And one of the ways that we've attacked this problem is to show that if you are training these parameter-efficient updates to a base model, if you modify the training procedure just a little bit, we showed that there's a way to get what we call routing vectors and build effectively a mixture of expert style model for free. So this is a model where you have a pool of these adapters, you have a router that takes activations at some particular layer and chooses which of the adapters to use. And the nice thing about this again is that you don't end up having to specify explicitly which adapter you want to use. You can just describe the task that you want the model to perform, and then based on the activations, the inner processing of the model, it chooses the appropriate specialized model for you. And importantly, it enables a generalization to new tasks. So even things that you don't have a specialist model in your pool for, we show that it can generalize quite well to new unseen tasks and capabilities. Okay, so now I'm going to kind of tackle what I think is the biggest leap in this direction, which is again, this question of generalization. If we have a pool of specialist models, but we want the aggregate system to perform something that we don't have perform a task that we don't have a specialist model for, how can we do that? How can we generalize to new settings? And to me, one of the most promising ways to do that is via model merging. And some of you may have come across model merging. Model merging, it just provides a way of combining models in hopes of combining their skills, combining their capabilities. And so to give you kind of a view of what that might look like, usually when we update models or when we want to get a model to attain new capabilities, we perform additional training, right? So we find a data set that corresponds to the task that we want the model to perform, and then we train on that data set. And that's kind of what's being shown on the top. Now, what merging allows you to do is to take models that have complementary capabilities and rapidly and very cheaply, without training, combine them to get an aggregate model that inherits the capabilities of the constituent models. Okay, so what does merging look like? Well, in the paper listed at the bottom here, we showed that you can view merging as the optimization problem shown at the top of the screen here. And if you make a common approximation in this optimization problem, there's a closed form solution. And I'll describe a very simple case of this closed form solution. It's just averaging the parameters of the models together. So if we have two models that share an architecture and we just average their parameters together, then we can perform something that looks like merging, that basically does what we want it to. And if you make some more sophisticated approximations, things can work a bit better, but the basic idea is there. We've also done a bit of work on more sophisticated merging schemes where we try to determine when the two models or however many models being merged kind of have parameters that conflict in some way. So if we average them, they would just get zeroed out. And so we prune some of those parameter values and have the non-pruned values kind of vote on what the sign of the merged value should be. And this produces a method called ties merging, which we showed works even better than doing simple parameter averaging. So the last point that I'll make is that if we want to build ecosystems in this way, and we want to make it easy for lots of people to contribute, then we need to build systems. And so I'll talk about two systems that we've built that make collaborative development of ecosystems like this easier. The first is called Git Theta, and Git Theta is a Git extension. Git is one of the most popular version control pieces of version control software, especially for keeping track of changes to code bases. And what Git Theta does is it extends Git so that it can keep track of updates to a model checkpoint. So as I perform parameter efficient fine-tuning or as I perform merges, Git Theta keeps track of all of that in a standard Git version tree. And Git Theta makes use of a Git LFS backend, so it's supported on any system, including, for example, GitHub or the Hugging Face Model Hub that has a Git LFS backend. We also built a system called Petals, and the goal of Petals is to enable inference and, to some extent, parameter-efficient fine-tuning of large models on volunteer computing. So in other words, if you have a volunteer who says, I'm willing to run inference on these layers of this model, and then you get enough volunteers to cover every layer of some particular model, Petals figures out how to route requests through them over the consumer internet and do inference efficiently. And notably, it does inference without requiring anything of the end user, of the person who actually wants to perform the inference, because it handles the routing of requests, and also the compute itself is given by volunteers. And because of the way it's architected, it also can enable parameter-efficient fine-tuning reasonably efficiently. So that's all I'll say about this work that we've been doing. If you find it interesting, feel free to contact me. And also, if you have any feedback on my talk, you're welcome to give me feedback on the link in the screen. Thanks a lot. Bye.
Hi, everyone. Thanks for having me, and I'm delighted by this opportunity to share our recent research about democratizing LLM training by exploiting low-rank gradient. I hope that could be of interest to this audience who are interested in decentralizing AI. Let's start by something everybody knows now. Large language models are so powerful. They help us do conversations, generate plausible content, form AI agent, do complicated reasoning, and even sophisticated planning tasks. But same well-known as their capability, everybody also knows training or even fine-tuning the best large language models is extraordinarily expensive and beyond most, if not almost everybody's resource availability. That comes with multiple bottlenecks. Training the best large language models need the highest end GPUs that cost money. And even the best GPUs will take days or months to train, and not to mention about the data and the human resource you need to pay for that efforts. So people sometimes say, in very soon, training language model will not only be beyond the individual's reach, but even beyond the reach of even small countries' budget. Our vision is to democratize the training of LLMs. We ask the question, beyond using the highest end GPUs, is it possible to democratize LM training with those cheaper ones, those consumer grade GPUs, not those expensive ones in the data center, but those available in your computer or even someday in your mobile phone? So we took a look comparing between those good GPUs, those top end GPUs such as H100, A100, those most popular in data centers, and the consumer grade GPUs. For example, the 4090 is a good GPU for gaming purpose, and you can often find it in good desktops. So comparing their specifics, we find that they are actually not too far away in terms of compute ability. For example, you can look at the FP16 compute performance between A100 and 4090. They are not too far away from each other. But the biggest difference lies in their memory and communication, which is necessary because nowadays LLM training involves massive dataset and huge storage for model parameters, gradients, and other training artifacts. So when you see such a big price difference between the high-end GPUs of H/A100 versus a consumer-grade GPUs, those 10, 20, or even hundreds times of differences, those are where you pay your money. You pay the money for GPU memory and communication, not necessarily for compute power. So looking at this limit, we realize that contradicts. So this seems to contradict with the current trend. If you talk to any LLM researcher, many will tell you scaling is all you need. That is, keep increasing model size will solve most of our research problems naturally. This is a topic on the debate, but there is no denying that it has become the common practice of most industry companies leading LLM research nowadays. So is there any chance that can save us from keep scaling the model while keeping the GPU memory war? Is there any chance we could use those consumer grade GPUs while scaling keeps to dominate? And our answer is there is a chance to mitigate between the two. You could keep enjoy your big model as long as you keep your gradient small, because it's the model and the gradient constitute the major training memory cost. So if you can reduce gradient, you can save more size for model scaling. Is that possible? Technically, it turns out yes, by discovering one fact, that is the inherent low rank phenomenon in LM gradients. When we talk about low rank, let's start from some arguably most familiar method regarding low ranking LM called low rank adaptation, or LoRA. It is a parameter efficient fine-tuning method. Given a pre-trained large language model such as Llama 7B, it will fine-tune the language model to fit a downstream domain by assuming the fine-tuned weight equal the summation of the original pre-trained weight and a weight delta, and this weight delta could be represented by a low-rank factorized format. And this low-rank factorization will save much space compared to the original dimension of the weight, and that's where LoRA could save you lots of memory. LoRA could have or become the de facto method in fine-tuning, but with certain caveats. Number one, LoRA could only fine-tune the model. It cannot pre-train a model from scratch. And number two, LoRA is a kind of ad hoc solution by assuming the weight delta to be low rank. It also changes the original optimization objective. So that motivates us to go beyond the LoRA and develop a new method called gradient low rank projection, or GALLO. GALLO is capable to save memory for both pre-training from scratch and fine-tuning. For the first time, it is able to reduce the pre-training memory cost of a Llama 7B model under 24 gigabit. That is below the memory of RTX 4090, a good custom consumer-grade GPU, which is encouraging for the first time. And by third-party evaluation, in fine-tuning cases, we also outperform other the existing solvers, such as 8-bit quantized ADAM-W, by using less than half of its memory and a higher tokens throughput and comparable or better results. So let's look at what Gallo does. It's a very simple algorithm, in fact. We have 3 steps. First, compute the gradient in the original space, and then project that into a low-rank space using the SVD of the past gradient, or in fact, other low-rank projectors are possible. So we usually choose the rank to be very slow, so the projected gradient is much smaller in size compared to the original. We do the update in this projected space, and after that, the update is projected back into the weight space and update the weight. So in this way, we are saving the grid. We are saving the optimization state and the projection weight, the optimization state from original full ranks 2MN into 2NR. Remember here, R is our rank. So compared to the original MAM, it could be thousands of times smaller. That's where the memory saving comes. With this simple 3-step recipe, project gradient, updating projected space, and projected back. Gallo is compatible with all the mainstream deep learning optimizers, such as ADAM or ADAM-W, because they could just be plugged in to be used in this projected space. Also, beyond an ad hoc method, Gallo is a provable method, and in our paper, we show that the gradient will be provably low rank. For large transformers, the weight trajectory is guaranteed to move in a few low-rank subspaces along the training, so it becomes principled. In pre-training, Gallo can pre-train a Llama 7B model with a token batch size of 256 on a single device, without active checkpointing and memory offloading. So that enables training Llama 7B on RTX 4090 for the first time. Also, we cite another third-party report on fine-tuning result. So people fine-tuned the Llama 7B model on the same consumer GPU 4090 with a 70 gigabit VRAM, and they found the loss curve dynamics to be almost identical with the full training, showing that Gallo is able to recover the full training dynamics. And that's also manifested in the close performance between Gallo's fine-tuning result versus the full tuning result. And remember, the full tuning result is thousands of times more expensive in memory compared to Gallo. And then compared to another method, the common method, LoRa, Gallo consistently perform on par or better. And because it's an attractive trade-off between memory and performance, Gallo has been popular in the open source community and implemented by leading open source libraries, including Hugging Face, PyTorch, and Llama Factory. Even further, our recent method has integrated Gallo with quantization. That is motivated by the observation that popular laptop GPUs, such as RTX 4060, are equipped with up to 16 gigabit of memory. So we set 16 gigabit memory as our next goal up to 24 gigabit. And we reach our goal by carefully study how to quantize each part of Gallo algorithm. We found that some part of Gallo algorithm, such as a projection step, can be deeply quantized without affecting the performance. And by reducing the memory cost further from 24 to 16 gigabit, we can fit the pre-training of Llama 7B into 4060 Ti, and that will reduce the price further by more than 3 times based on the price as of August 2023 in GPU hardware. And Gallo has this new algorithm we call QGallo has further pushed the boundary of memory performance trade-off. At the pre-training stage, our new algorithm facilitated training a 7B model from scratch on a single 4060 Ti with only 16 gigabit memory. At fine-tuning, it reduced memory consumption also by 50% compared to LoRa and Gallo, while consistently outperforming QLoRa, another quantized fine-tuning solution, by a large margin at the same memory cost. With that, I hope to share you with our vision that in one day, everybody should be able to train their own language models with their own GPUs, however many and wherever they are. And I would like to attribute the thanks to my collaborators, and thank you for your attention. Bye.